All right. Today we're going to talk about the PID control and dynamic stable. And first, what is P and I and D means in PID? P means proportional, I means integral, D is the derivatives. And those three are means describe how the arrows term is handled. And the PID control is simple, efficient, and effective in a wide area of applications. In fact, it's majority of controller types and industrial applications. Why we need a feedback control? First, I need to go for what is let's go for an open loop system. We have input acting on a plant, and then come with output. Actually, if we have like a kind of robot, we wanted to hit the target over here, the X, but it may go here, it may just go here and stop here, it may go somewhere else, and there's no way we can adjust it. And that's why we need a controller to tell. While we're having a controller, we'll have a reference. And I will still have a plan over here. I will have some output, and the controller will goes back and tells there's an error. And then the robot will adjust himself, and then and then and this is a feedback controller. It just the signal goes back to the reference and tell, oh, there's a difference, and then there's an error over there, and then we need to adjust it. And I have created a simple system that to show how PID influence the control system. Before, like at the first, there's the PID control are all zero. There's no control on the system. Then we'll have the system, the step response for settling time at 4.6 seconds and the final value at 0.5. And actually, we wanted to hit 1, and actually this settling time is not good. We want it to be as fast as possible, and this is 4.6 is definitely not good. And then I have adjust the P control. I set the P control to 1, 5, 10, and 20, and the rest of the integral control and derivatives control are still 0, remains 0, and the rising time goes faster and faster. As you can see, the slope, it actually goes faster and faster. And the settling time stay at the same after we set the P controller to 5, and like 5, 10, 20, what this term I forgot what number I set, but they are kind of remain the same. And then after we increase the P control, and we can see the overshoot, it just goes higher and gets bigger and bigger, and that's not what we want. And then after this, if we want to reduce the overshoot, we need to implement the D control, derivatives control. When we have the KD value gets larger, and the overshoot will get smaller and smaller and smaller. And the settling time have tremendously reduced, and we can see the final value start hitting 0.952, and that's a good sign because we want to hit exactly to 1. And right here, we set the KP to 20, P controller to 20. We set the okay, that's the D controller. We set the D controller to 10, and we have the integral control coming in, and I set it to 1. And turns out we have a really nice system that having a steady state value equals to 1, and there's no overshoot, and then the settling time is good, the rising time is good. Next, I'm going to talk about the PI with the velocity input, and actually in this system, we'll get the omega and all of these two terms, and then the root of the characteristic equation will come to with this, and then in both, and if we want the system stable, and we want to keep both the Kp and Ki bigger than 0. And for a PID control, we're gonna have a 3-order system, and then we wanted the 3 of them is larger than 0, and we want the Kp times Kd is larger than Ki. Okay. And after this, let's go and for example, and this is example from the exam review, the final exam review that provided in the class, and it's the first problem is actually just a linearization problem from we just need to linearize the system, and I'm not going to go through it. And then if we set the theta equals to 0, we will have a linearized system equals to this. And then let's just directly go to the second problem. Okay, the first problem. I think I changed something. Okay, so from the previous system, we have the linearized one be stable around the theta d equals to 0, use a P controller. If your answer is yes for at such a controller, if no, then say why no such controller exists. First, we're gonna write down this tau equals to Kp equals to our theta d desired minus the theta, and then the theta d minus theta is equals to theta e. That's the arrow. Then we have our linearized system writing down like this. I'll write it down right here. Theta dot plus k theta, and will equals to tau, and actually the tau equals to Kp. And then we move the term, then we will have theta dot plus k theta equals to Kp. Oh, sorry about this. We have theta dot plus the k plus the Kp. Theta equals to 0. And then the question is asking, can the previous system be stabilized around theta d equals to 0 by using a P controller to make sure that this system is stable? We need to have the answer is for this problem is no, because the coefficient of the theta dot term is 0. So yeah, for this question, the answer is no. And we go to the next problem, and then right now we're going to deal with a PID controller. We have a theta d equals to c, which c is larger than 0. It's a given constant. We're using our old the system that we already had. Right now, and then we're also with a feedback linearization that achieved the goal. So first we have a tau There's a K sine theta. That's for the feedback linearization. That's why we have a K times the sine theta term right here. And then we have the Kp times the theta E. That's the P control. Then we have a Ki, the theta E ds. That's our integral control. And we have a derivative control. That's theta dot E. There you go. Then, also we have the theta E is equals to the theta desire minus the theta. And then the theta E dot, we'll have it equals to minus theta dot. So right now we will have, we put this term in, then we have the theta dot plus K sine theta equals to K sine theta plus Kp theta E plus Ki. After this, actually you can remove this K sine theta term, and then we'll have theta dot equals to minus Kp theta E minus Kd theta dot E minus Ki. Then with the derivatives, this equation, then we have the theta E dot plus Kp theta E dot plus Kd theta dot E and plus Ki theta E equals to 0. If you want to stabilize the system, and from the previous slides, we'll need to have this. So right here, we need to have the Kp, Kd, and Ki is larger than 0, and another is the Kp times Kd should be larger than Ki. And that's it for this example, and thanks for watching. Y'all have a great day.